Okay, in this video, you will discuss on one example of DC analysis for Zener diode voltage regulator. So we consider this very simple Zener diode voltage regulator circuit consists of supply voltage, and then we have the R here. This is actually the supply resistance, and then we have the load resistor. So the load resistor is connected in parallel with the Zener diode. So here the supply voltage is 12 volt, and then R here is 500 ohm. Okay, VSAG is equal to 5 volt, and then RL is equal to 4.5 kilo ohm. So and we have another specification, YSAG mean and P max. So YSAG means is the minimum Zener current where the diode is on state. So in order for the Zener diode to be on and operate as a regulator, the Zener current need to be higher than 0.1. So Pmax is actually the power consumption, the maximum power consumption of the Zener diode. Above this value, so there is very high possibility that the Zener will broken down. Okay, the first one is examine whether Zener diode is on and can constantly operate as regulator without any damage. So the condition is we want to examine whether Zener diode is on, and another one whether it can operate without any damage. So this is related to YSAG mean, because the YSAG need to be higher than YSAG mean, and this is related to Pmax. Okay, so what can be done is here for the first question you need to analyze what is the YSAG value. What is the YSAG value? Okay, YSAG value, in order to calculate the YSAG value, so let's use the approach using the Thevenin theorem. So this circuit can be redrawn as this circuit. Yeah, so this is 12 volt, this is 500, this is 4.5k, this is the Zener diode VSAG. So it can be further simplified using Thevenin. So when you use the Thevenin, you will only have VThevenin and RThevenin. Okay. So and then the current here, this is a very simple series circuit. So the current at in this series circuit is equal to YSAG. Okay, because this is YSAG, because this is the current across the Zener diode. So the calculation for VTH is equal to, using the voltage divider, 4.5k over 4.5k plus 500 times 12. So we get a 10.8 volt. And then RTH is equal to 4.5k parallel with 500. So this is, we do the calculation, we should get 450 ohm. So once you get this value, you can apply the KVL to get the YSAG. So let's do the KVL. KVL, this is minus, let's start with the VTH, minus 10.8, this is 10.8, and then plus YSAG times 450 ohm, and then plus VSAG. So voltage across the Zener is Vz. So Vz is equal to 5. So plus 5 equal to 0. So now you get the Iz equal to 10.8 minus 5 over 450. So this is equal to 12.89 milliampere. So you get the value for Iz. So here Iz is equal to 12.89 milliampere. So this is much higher than Iz mean. So this means that the Zener is on. And then we can calculate the power of the Zener diode. The power is P equal to IV, Iz, Vz. This is 12.89 times Vz is 5. This is equal to 64.45 milliwatt. So here this value is Pz is lower than Pmax. So means that Zener is okay or in safe operation. Okay, so this is the answer for question number 1. Okay, so the question number 1, you want to examine whether the Zener diode is on and whether it can constantly operate as a regulator without any damage. So the answer is yes, the Zener diode is on because the Zener current is larger than Iz mean. And yes, the Zener can operate without any damage because the power consumption or power dissipation of the Zener is much lower than the maximum power consumption or the rating power. And the last one is the second question is you need to calculate the current at load resistor. Okay, for the current at load resistor, it's quite simple. The second question, you see that because the Zener is on, the voltage at the Zener will be equal to Vz will be equal to 5 volt. Okay, and Zener is parallel with the RL. So therefore the V out will be equal to Vz. Okay, so will be equal to 5 volt. And then we can have this equation, V out is equal to IRL. IRL is the current across the IRL times RL. So this is now is 5 equal to IRL 4.5K. So IRL is equal to 5 over 4.5K. This is equal to 1.11 milliampere. Okay, so this is the answer for the second question. There's another way how you can analyze this circuit by using a node analysis. So instead of using Thevenin theorem, you can use node analysis. So we will do the node analysis for this node. Yeah, for this node. Okay, so we have the Vs, the supply voltage is 12 volt, and then R is 500 ohm, RL is 4.5 kilo ohm, and then Vz is equal to 5 volt. Okay, here when you do the node analysis, first you assume that the Zener is on. So when you assume Zener is on, so the voltage across the Zener diode will be equal to the VZ, which is 5 volt. So the Zener is 5 volt, and then another one is the V out should be equal to 5 volt as well, because the V out and Zener is in parallel. Okay, so next, in order to do the node analysis, let's label the current flow. Okay, let's put this is the IS here, and then the Zener is IZ, and then this is IRL. Okay, so for node analysis, start with KCL, Kirchhoff current law. So KCL is for this node, the entering current is I5, I say IS. So this is equal to IZ plus IRL. Okay, and then for each current, you apply the Ohm's law. So for example, IS, what is IS? IS is voltage over the voltage across this the VS to this node. Okay, VS to this node, and then you can get this one is let's say this is plus 5 volt. So this is 5 plus 5 volt. So this node is plus 5 volt. So IS is equal to 12 minus 5 over 500. And then for IZ here is this is not a passive component or resistor, so you cannot apply the Ohm's law. So this is IZ. And then IRL is 5 over 4.5. So with that, you can get the value for IZ is equal to this is 12 minus 5 is 7. Okay, 7 over 500. Okay, 7 plus over 500, and then minus 5 over 4.5. Sorry, this is kilo. This is kilo. So this is equal to, let me calculate. Okay, 7 over 500 ohm, 0.5 equal to, this is 14 milli minus 5 over 4.5, this is 1.11 milli. So the IZ is 14 minus 1.11. So this is equal to 12.89 milliampere. So you get here the IZ is larger than IZ min, because IZ min is 0.1 milli, this is 12, so Zener is on. So how about the maximum limitation? So the given parameters is Pmax. Okay, Pmax is 400 milliwatt. So here from the Pmax you can get IZ max. IZ max is 400 milli over 5. So this is 80 milliampere. Okay, so IZ is lower than IZ max. So save operation. Okay, for IRL, actually you have calculated the IRL in the KCL is equal to 5 over 4.5K, which is 1.11 milliampere.